السلام عليكم ورحمة الله تعالى وبركاته. In this video, I will explain the spectrum of AM wave. As we have seen from the previous video, that the AM signal can be expressed as follows. S of t is equal to AC cosine omega ct plus mu AC over 2 cosine omega c minus omega m plus mu AC over 2 cosine omega c plus omega mt. So in the above equation, the first term represents the unmodulated carrier or the pure carrier signal, which it has a frequency of omega c and an amplitude of AC. The second term, mu AC over 2 cosine omega c minus omega mt, represents the lower side band, and the last term represents the upper side bands. Both the upper side band and lower side band has an amplitude of mu AC over 2, where mu, as we have seen earlier, is the modulating index and can be expressed as the ratio between the maximum amplitude of the necessary signal divided by the maximum amplitude of the carrier signal. So note that omega c is equal to 2 pi fc and omega m is equal to 2 pi fm. Hence we can write S of t in terms of frequency in hertz instead of omega. So S of t will become or can be expressed as AC cosine 2 pi fc t. This is for the pure carrier or unmodulated carrier signal, plus mu AC over 2 cosine 2 pi fc minus fm for lower side band, plus mu AC over 2 cosine 2 pi fc plus fmt for the upper side band. So the spectrum of the AM wave, as shown here in the figure, has three frequency components. One for the carrier signal, which has a frequency FC and amplitude AC, while the upper side band has located at a frequency of FC plus FM, and it has an amplitude UAC over 2, and a lower side band which has a frequency FC minus FM and an amplitude mu AC over 2. So this represents the upper side band, this represents the lower side band, and this component represents the pure or the unmodulated carrier. So this figure contains the carrier or the full carrier and both the side bands, the carrier, and both the side bands, upper side bands and lower side bands. Hence it is called double sideband full carrier system, DSBFC. From the figure, as we can see here, the bandwidth of the signal, of the AM signal, can be obtained by taking the difference between the highest frequency component and the lowest frequency component of the signal. So from the figure, we can obtain the bandwidth of the AM as follows. The bandwidth is equal to the difference between the upper side band frequency minus the lower side band frequency. So BW stands for the bandwidth, equal to FUSB, upper side band, minus the FLSB is the frequency of the lower side band. So if we substitute the upper side band frequency, which is FC plus FM, minus the lower side band frequency, which is Fc minus Fm. So we can find that the bandwidth is equal to 2Fm. So as we said, the bandwidth of the AM wave is equal to twice the bandwidth of the message signal or the modulating signal FM. So this is considered as a waste of bandwidth. That's because we use twice the bandwidth of the original modulating or the message signals. That's one of the drawbacks of the amplitude modulation technique. Also, we notice another major drawbacks of the amplitude modulation, a waste of power, because we transmit the carrier or the pure carrier signal within the amplitude modulated signal. So most of the power is within the pure carrier, and the carrier signal carries no information. It has no information in this signal. So this is also considered one of the drawbacks. So the two major drawbacks of the amplitude modulation technique is a waste of bandwidth and a waste of power because of the pure carrier signal. Modulation index. Amplitude modulation index describes how the amplitude of the carrier signal and the message signal affects the amplitude of the AM signal. And as we have seen previously, mu is equal to the, or given by the maximum amplitude of the ratio between the maximum amplitude of the message signal to the amplitude of the carrier signal. So let us show the importance of the modulation index. So mu is equal to AM over AC, where AM is the amplitude of the message signal and AC the amplitude of the carrier signal. So from this figure at the right hand side, we have the message signal, which has a single frequency, and we have a carrier signal which has a high frequency compared to the message signal, and here the resultant amplitude modulated signal. So here we have AC plus AM, which is the maximum amplitude of the AM, and here at this trough is the minimum amplitude of the AM wave, which is equal to AC minus AM. So the maximum amplitude of the AM wave is equal to AC plus AM, while the minimum amplitude of the AM wave is equal to AC minus AM. So A max is equal to AC plus AM, and A minimum is equal to AC minus AM. If we add these two equations together, we will have A max plus A minimum equal to AM minus AM will be cancelled, and we will have 2AC. So AC is equal to A max plus A minimum divided by 2. Likewise, if we subtract these two equations, or we subtract the A minimum from A max, we will have AM is equal to A max minus A minimum divided by 2. So we know that mu is equal to AM over AC. If we substitute AM and AC in this expression, we will have mu is equal to A max minus A minimum divided by A max plus A minimum. So this is another expression for the modulation index. Okay. Based on the modulation index, we have three types of modulation. We have under modulation, ideal modulation, and over modulation. Under modulation occurs when the amplitude of the message signal is less than the amplitude of the carrier signal. So if AM is less than AC, then mu will be less than unity or less than 1. While if the amplitude of the message signal is equal to AC, then here mu will become equal to 1 exactly. And this is, we call it 100% modulation. And this is for the ideal modulation. And if AM, the amplitude of the message signal or the modulating signal, is greater than the amplitude of the carrier signal, and in this case mu will become or will be more than 1 or greater than 1. So let us examine each case for the modulation index. Okay, so the standard case or the under modulation, when AM, the amplitude of the message signal, is less than the amplitude of the carrier, that means mu is greater than 0 and less than 1. So in this case, we will have the modulated signal which have the following shape. We will have here, this is the maximum or A max, and we will have the minimum value, A minimum, which will be above the 0 level. So here we have the standard, and we can extract the message which is buried on the envelope of the AM wave. When AM is equal to AC, that means mu is equal to 1, then we will have 0 values here, because we have A minimum is equal to AM, AC minus AM, and while AM is equal to AC, then this will become 0. So still we can recover the message without any distortions in this case, as well as in the first case when AM is less than AC. But when AM is greater than AC, that means mu will be greater than 1, and in this case we will have a distortions because of the phase reversal. The carrier signal will be reversed by 180 degrees, so a phase reversal will occur. This result in loss of information and distortions, and accordingly loss of information. And in this case, we cannot recover the message signal using a simple detector at the receiver side to demodulate the signal, to extract the message signal from the amplitude modulated signal. Thank you.